Okay, let's get started. Hi everyone. 4 of you, welcome to those of who come to in-person discussion session. And last week we learned a little bit about the binary search tree for 2 lectures, and 1 lecture we learned about generics. But since the binary search tree is the additional 1 data structure we learned apart from the W linked list, the linked list. So for this discussion session, I will spend a huge amount of time to talk about the binary search trees. So, so in this discussion problem set, we are going to review the concept of binary search tree and several useful manipulation methods on this data structure, such as insertion, deletion, and query. And we will also contemplate how the binary search tree will be beneficial to some operation compared with some other data structure we have already learned. So, so let's start by recognize the binary search tree. Oh, by the way, please download this file on the Piazza. I send an email to everyone using Piazza. And I create a mega thread of every single week's discussion and with their problem set and their solutions. And I think that will be an amazing resources for you to review once like the quarter ends for the final exam. So there's 2 definitions. For the first one is for balanced tree, and the second one is for complete tree. So the tree is balanced. Did the professor cover the balanced tree on the class? Oh, kind of. So so here is like a formal definition of the balanced tree. So the balanced tree is so first of all, an empty tree is height balanced. So it's already balanced. So a non-empty binary tree T is balanced of the first of all, the left subtree of the T is balanced, and the right subtree of the T is balanced, and the difference between the heights of the left subtree and right subtree is not more than 1. So we can apply this idea recursively. So we see that the third one, this one is the core idea, right? The difference between the height of the left subtree and right subtree is not different than 1. Meaning that, for example, if I have a binary search tree like that, that is not balanced because the height of the left subtree of the root is 3, while the right subtree of the root is 1. But the reason why we have the first 2 concepts here, the left subtree of T is balanced and the right subtree of the T is balanced, is if we focus on this subtree. So this is a subtree, right? If we focus on this specific node, this node is balanced. But we need to apply this rule recursively all the way up to the root nodes to see whether the tree is balanced or not. I know it might be a little bit confusing right now, and we will see a lot more examples of the actual binary search tree we are evaluating. So that's for the balance tree. Any question for the balance? So does it mean if there's like 2 on this end and 1 on this end, since the difference is like 1, like it will be balanced? Yeah, this one will be balanced. Yeah. So the reason behind like why we consider this tree was balanced, because so first of all, that's the definition of balance. So it's only the difference, it's not that more than 1. But second of all, sometimes we are inserting stuff into the binary search tree, right? So this is considered a half complete, like the binary tree. So it's still balanced, but it's not complete. So that is like an intermediate state of the tree, right? So we will reach that a tree most optimistically. And so naturally, when we come to the complete tree, so the complete tree is which all the levels are completely filled except possibly the lowest one, which is filled from the left. So yeah, so a complete binary tree is just like a full binary tree, but with 2 major differences. So all the leaf elements must be lean toward left, and the last element, wait. Tree doesn't have to be a full binary tree. Oh yeah, so yeah, sorry. There's two definitions here. So there's full binary tree and complete binary tree. So the complete binary tree is all the level is completely filled. So that one is completely filled. So the first level is completely filled with the root node. And the second level is also completely filled because we only have two nodes. And the third level, which is the leaf level, right? It's not completely filled, but we also consider that as complete. But because the rule says that which all the levels are completely filled except possibly the lowest one. So the third one is the lowest one. So if I have a tree like that, that's a full tree. That means every single level is filled. But if I have a tree look something like that, that is not complete because it's not full from the left. But I have a feeling that I'm introducing this idea of complete a little bit early, but you will learn more about the complete tree when you learn another data structure which is called heap. So yeah, sorry. So let's apply that concept to some trees, the actual trees. So choose from the list of options that is best describe this data structure. So this multiple choice question. And choose, there might be multiple answers. So, okay, think about 30 seconds about whether this tree is following the 4 categories. Okay, so first of all, is it a general tree? This is a general tree, right? So there's no like self loop. There's no like a large loop behind that. So this is considered a general tree. Is it a binary search tree? So it is a binary search tree because of the property of the binary search tree, right? All the elements from the right-hand side of the root of the node is larger than the node itself. So from here, we can see that 87 is larger than 87 is larger than 51, but 52 is less than 87. So it's on the left branch of the tree, and that applies to every single node of the tree. So for the third one, is it complete? No, it's not complete. The reason why it's not complete? Yeah. So correct. So because each level is not completely filled, so I have like empty slot here and empty slot here. If those two, and another one is here. If those 3 nodes are added, then this tree is complete. Yeah, right child of 1. Yeah. Those 4 nodes. Yeah. Yeah, no, sorry. Yeah, you need the right child. Yeah, sorry. The right one? This one? So the definition of complete has one special case of, so all levels are completely filled except the last level. So the last level is not, even though we have like an empty child of this one, but we are filling everything from the left-hand side. So it's complete. It's considered complete, but it's not an important point here for the binary search tree. So this property might be important for another data structure, but we will cover that later on in the further. Yeah. So it is a balanced tree? Is it a balanced tree? Raise your hand if you think it's a balanced tree. Okay, so the balanced tree is, I quickly go over the definition before when we're beginning. So the left subtree of the T is balanced, right subtree of the T is balanced, and difference between the left subtree and right subtree, the height is not than 1, not larger than 1. So okay, raise your hand if you think it's balanced. Raise your hand if you think it's not balanced. Okay, yeah, sure, 50-50. So let's see, okay? If I want to check the root node here, what is the height of the left subtree? 3, right? What is the right subtree? Also 3. So upon this point, we are considering it as a balanced tree, right? But only the first node. What about the 87? What is the height on the left? So it's 2. What about right? 0. Right hand side is 0 because it's empty, right? So it's also considered as unbalanced tree.
Oh, I misunderstood the definition. I thought it was like right tree. So because like if you look at the left side of the root, that height is 3, right?
Yeah.
Right side.
It's also 3.
The height is 3. I thought that that period is balanced.
Yes. So so if we go over, so for the student who listening to the podcast, yeah, the rules of the balance is we are applying this rule recursively. So the third rule is the golden rules, and we need to apply that rules for every single node. Yes. So correct. So you need to apply this rule recursively. Make sure every single subtree, every single node, the left subtree and right subtree is balanced, so that the whole tree is balanced. Because why? So if the reason why we have that definition is if we have this extreme case. So for example, this is the root node, and I have a tree like that, and I have another tree like that. Well, it's not a right branch like that. So this is considered balanced at the root node, right? But every single node down the level is not balanced at all. Okay, so right now we have an extreme case. So consider the following options from this tree. Well, first of all, is it a tree? This is a general tree, right? Is it a binary tree? Binary search tree? Yeah. This is a binary tree because, so this is only on the right branch. The 10 is the smallest element, and each step to the right is increasing. 10, 30, 34, 45, and 56. Is it a complete tree? Is it a balanced tree? So we call this very unbalanced tree. So the reason why we use a binary search tree because we want our data structure to be balanced, so that the height is minimized, and so that the other comparison, for example, insertion and deletion, will be faster. So I want you to think about this data structure, like here. What other data structure do you think is like one of the we learned? Yes. So if we use the binary search tree in this extreme case, we're actually turning the binary search tree into a linked list, so that we are losing a lot of nice property of binary search tree. So if we have time, we can come back to talk about like what property did we lost, and like how this is hurt our performance, and like how we could avoid that. Okay, the third one. Is it a general tree? Binary search tree? Yes, it is a binary search tree. Because you will do it in the exam without me talking about it. Is it complete? Is it balanced? Yeah. So I want to give a nice impression of the perfect tree. This is the perfect tree in our mind that contains the most amount of element, but with minimized height. Yeah. So it is very efficient in terms of insertion and deletions, because when we talk about time complexities, what is the time complexity of finding an element in here? Log n, right? We don't have the n in front of the log n, so it's just log n. And to understand where the log n come from, the optimal height of the binary search tree is actually log n. And so here, right, we have in total 1, 2, 3, 4, 5, 6, 7 elements in it. The height is 3, right? So for a binary search tree, for a complete binary search tree, because each node has 2 children, that's why we call it binary. So the height will be 2 to the, So a height is 2, right? Yeah, it's 2, sorry. So height is 2. So the total number of the nodes with the height is the 2 m plus, if we denote this as h, so it's 2h plus 1 minus 1. And equals to the n. That's the total amount of node that I have, right? So if h equals to 2, so it's 2 to the 3rd power, which is 8, minus 1 equals to 7. So if this complete tree, the height will be log base 2n, right? And there might be add 1 and minus 1 to it, but it doesn't matter, because in terms of the time complexities, we only care about is the logarithmic time. But so the number of comparison to find an element or to insert an element, to delete an element, is essentially the height of the tree, right? Because what I'm doing is, if I compare with this node already, if my target is 52, let's say, because it's larger than 51, I can discard all the left branch, right? So this discard, this confidence that I make, or the premises I make on the left branch, that all the element on the left branch is smaller than 51, but item I search is larger than the 52 or 51. So I could make that deletions. But let's say I have an extreme case on this. I want to find 45. I don't have that nice property because there's no left branch because it's so unbalanced. And it's made comparison by a lot, right? So worst case here, we only need to make 3 comparisons. The root, first level, and second level. And the worst case here will be 1, 2, 3, 4, 5. Yeah. What? Yeah, this is the ON. Yeah. Any questions?
Is the worst case be that the element is not there, or the very last one?
So
We're searching
in that one, worst case is always is always linear, because you can think about this. Let's say this is the element I want to search, right? I need to go over all the n element. And if the element is not in my binary search tree, I need to go over all the n, right? Let's say my element is at the second last element. Let's say I have an n element binary search tree. How many elements I need to compare? N minus 2, right? So regardless of how is the last term, like whether it's not did not exist, or exists the last one, or the second last one, or the third last one. The second or third or large, the third is a constant term, right? It's an O. Yeah, it's like a big O of n minus some constant c, right? As long as the c is not the exact n, which is a constant time, the c we could ignore that because it grows like a linear time. Yeah. Okay, what about this one? Is it a general tree?
I thought that was the definition of a binary tree. The general tree, yes.
So this is a general tree. So a tree can have whatever children you want. It can have like 1,000 children. It's also a tree. So the definition of a general tree is as long as it don't have like this kind of connections. It don't have a self loop. And this is a general tree because you see like growing like inverted down tree shapes, right? But this is not a binary tree, right? Because it's every single node might have 3 or more children. So it's not binary, not even a search tree. And is it complete? So the definition of complete tree is except for the last level, every single level is filled. And for the last level, every single node needed to fill from the left. No, right? Because of those two, no. If I either remove those, then it will be complete. Or I can move into here. Yeah. Pardon? No, it doesn't. It doesn't specify that. Yeah, you could have random number of children, and well, for a general tree, yes, the concept of tree is very flexible, and yeah, you could have whatever number of children in a general tree. So if I limit the amount of children I have, like for this node, for example, this is in this case is 3 children. Right? This is called a three array tree. Yeah, it's like not binary anymore, it's 3 array. And yeah, actually in the later on PA, you will actually implement something like this. So yeah, okay, is it balanced? Is it a balanced tree? Raise your hand if you think it's a balanced tree. Okay, let's check. Let's check. So let's focus on the root node. So this child has like a height of 2, right? This has 1, and this has 2. So as long as the root node if satisfies the balanced tree criteria. And same thing applies for 24 because right here is also 0 and 0. So it's not different than 1, larger than 1. The same applies to the 12 and 87. So it is balanced tree. Yeah, it is. It's confusing, right? Yeah, but the definition is left height and right height is not different than 1. So I don't have like something like so this one is balanced, but if I add additional level, it's not balanced. Or in other words, this one is imbalanced because I have the right hand side has a 0 height, left hand side has a height of 2. Yeah. Any question? I know it's confusing. Tree theory. All right, insertion and deletions. So, yeah, like the tree, it looks good. If I want to delete the 51, so what is the final shape of the what is shape of the final tree? And use the in-order successor as a node of replacement. So, what is the meaning of in-order successors? Yeah, it is 52. Yeah, it is 52. Yeah, so it's the leftmost child of the right child. Yeah. Yes. Yes, correct. So in order means that I want to have this order informations. And in order successors means that the one behind it. So if I want to delete 51, I want to move 52 out to the node, out to the root, right? Yeah. So right now, this is 52. And then what is, how should I deal with the empty slot of the 52? Yes, so put 83 up here, right? Yeah, so that is the final shape of the, for the binary search tree after deletions. So the reason why we specify in-order successors is, so during grading process, we want to have consistencies so that we could grade quicker. So pay attention to the in-order successors. So in exam, you might also ask for the replacement node of the in-order predecessors. So that would be the rightmost child of the left child. I know it's confusing. Yeah, so one way to think about this, so the way I learned it when I took this class is, so in-order successors, so successors means that it's behind me, right? So it's larger than me. So I need to step right, one step. And I go extreme, so step all the way to the left. So it's like, go right one step, and go all the way to the left. And you will apply that idea when you actually implement the binary search trees. Any question for the deletions in binary search tree? So are you doing the search like on all the nodes, or on every single node, like to search the one is the least larger?
So the way I did it in my head was I looked at it and I sorted the elements like in my head, and I was like, okay, 52 is the one that's directly greater than the 51.
Yeah.
It comes right after it. So that's how I know that that's the successor.
Yeah, that also works. Yeah, so that is the exact meaning of the in-order successors. But on this like stepping, like walking from the right branch to all the way to the left branch is a like algorithmical way to find the in-order successors. Yeah. So the whole premises of you are able to do this deletion is under the premises of this is a binary search tree. Because if I don't make the premises of this is a binary search tree, then the element of 52 can be at random places, right? Can be at 52, at here. And I will never able to find it, other than doing a brute force search on every single element. Yeah. We won't be that despicable. Okay, it seems that I forgot the insertion part, but do we want to do a practice on insertion? Yeah, sure. Okay. Let's see. Let's say I want to insert 85 into this binary search tree? What is the path that I need to be comparing every single node? What node I will be comparing, and like, what is the parent node of 85? So for what node I need to compare are first? 51. And then I go where? Yeah, and then 87. And then left, and then? So I put right here, right? Yeah. Yeah. So you need to put 85 here, and you are making this comparison from all the way from the root node to the leaf node to find an available position for it to find. So so that's a duplicate element, right? If an element is duplicate, usually we make the premises of the binary search tree has unique key. And the reason why we make that assumption is there might be ambiguous for another 83, whether it should be the left branch or right branch. And there are two approaches to that. One approach is just to consistently keep your approach. For example, if you have a duplicate element, always put it on the right branch, or always put it on the left branch. Yeah, just be consistent. And another approach is like when you are actually designing this data structure, you have the ability to like decide whatever put inside each node, right? So 83 is like a name of the containers. The container itself can have more like reference to it or element in it or data in it. So I can add another attribute. It says count. And if I found an existing duplicate element, I just do count equals to 2. So I know that I have 283. Does that make sense? Yeah, any question about deletion and insertion? It's rather straightforward. And for query, so you find a specific element, whether it's in the binary search tree, basically you just redo the insertion and like check element each by each and change the condition to whether it's equal to the target. Okay, let's get to the fun part. In order, pre-order, and post-order transversal. I don't know, when I took this class, this is the most confusing part. And the reason why it's confusing is like, they looks very similar. They only have 3 lines of code. And they're all doing it using an idea of recursion. So I put the code of in-order, traversal, pre-order, and post-order here. You could play around with it when you go back home to see this, like what are the difference. But if we pay attention to all the differences between them, first of all, it consists of 2 recursive calls, right? Every single traversal. Those highlighted in purple are the recursive call. So, like in IntelliJ, it has like something like that of sign when you actually do a recursive call. And the second thing here is the visit. That's visit, right? I'm actually visit this node. And the way I visit it is just print out the key. Or I could do something else. Or I can update the count or whatever. But this is really up to you. But this is the way. For the demo, I visit visit this node. So the most straightforward understanding of the in-order traversal and those 3 kinds of traversal is the in-order is the visit is between each in-order, right? It's between the, shoot, give me 1 second. Yeah, the visit is between those 2 the recursive call. And the pre-order is the visit is before those traversal call. And the post is just after. So those two traversal, the recursive call will actually help me to reach every single node in my tree. But we will do like keep track of the how it's called, so don't worry. So before we actually do the trace, so let's do a 3 pop quiz. So the first question is, in post-order traversal, the root node will always be the first one visited. Is that true? So here's the post-order. Whether the root node will be always be the first one. Yeah. This one is false. Why? Yeah. So in post-order traversal, when we visit the root node? The last, right? We visit the root node at the very last. So this is the last element we visit. So in pre-order traversal, the root will always be the first element we visit. Is that true? Yes, so that's true, right? Because whenever I do pre-order, without doing any traversal, I'm visiting this node already. So I'm already visiting the node before I traverse down to the root, down to the tree. So that one is true. Third one is a little bit tricky. So in order traversal, the root node will always be the middle element visited in all visit sequence. Is that true or false? Raise your hand if you think it's true. False? Okay, 50-50. This is a trick question, and this is a question that's good for final exam, right? So in order traversal, we are traversing between the call, right? So the reason why we call it in order traversal is we are traversing through each individual node by their value. So what if I have a tree like this? So the root node will be the first one I visit, right? Because it don't have left branch. This is a trick question. Don't get me wrong. The in-order traversal is just printing out element by their value. So real quick, in-order traversal on this tree is just 10, 30, 34, 45, right? Going on. Okay, I'll ask you another question. Then, since I told you that this case, this is false. What is the shape of the binary tree that the root node in order traversal is the middle element visited? Yeah, partially right. What if I have a tree like that? 1, 2, 3, and 4.
So it would just go 1, 2, 3, 4.
What about I have like a 0 here? Then it's not a center element, right? Like.
I think it has to be bound, complete, and
So it doesn't have to be complete. So that's yeah.
the number of nodes on the left
Yeah,
side.
correct. So I need to have a binary search tree that the number of node on the left branch is equals to the number of node in the right branch. That not necessarily the height. So the reason why is because all the element less than the root is on the left branch, right? So I will visit those nodes first before the root. And then all the element larger than the root will be on the right branch. So let's say I have 10 elements less than the root, and 10 elements larger than the root. So the root will be the median, right? Yeah. Well, what I can do, I could.
I didn't think of the linked list example. I always think perfect tree. So does it have to be complete?
No, it doesn't have to be. Yeah, because
Is there like a definite, like a word for saying that? Because it's gonna have a certain number here and a certain
no, I don't.
there, and the root's gonna be in the middle.
Yeah. So the thing is the perfect the complete full tree, which is every single level is filled. The full tree has that property. But some other tree that's not full is also has that property. Like I could do this and this is not full, but the root is also the middle elements, right? Yeah. Any questions? That seems to me a very good question for a final exam. We'll see. We'll see. Okay, let's actually do this. So in order traversal for this tree, I will. Don't be scared. You're doing good.
Let's be scared together.
So let me paste things here. This is in order. And what is the first node I ever visit? No, the visit. The meaning of visit is the print statement. Yeah, 1. And then 12. 32. Yeah, I guess you got the idea, just from the smallest to largest. But really, what I really wanted you to think is write down something like this. Okay, follow me. This is like a line, right? And this is node 51. And I do in order on node 51. And I didn't print anything out. And then I step to the left, because I have in order node left from that, right? So I do node 12, correct? But I still didn't visit anything, right? So it's node 1. Did you see how I do like a indentation here? Yeah, that really helps you to visualize the process of recursion. So the reason why in order is so simple, because we know that the output must be in order. But if I give you another like slightly changed one, it'll be really hard to track. So the node 1, because node 1 here and right will have no children. It's like a lonely node, right? So I hit the base case. The base case is no equals to no. Because this node, the left is no. And the right is also no, right? So it will hit the base case and then print out the element. So the first element will be 1. And actually this one will be that short, right? Because I finished the node in 1. But I still didn't finish node 12. So this is the in order on the left, right? I step to the left. And then what should I do next? Print 12, right? So then 12. Then what is another step after the print? Step to the right, right? So I have another call here with the same indentation as the yellow line. You write down node 43. And then 43, you need to step left first. So I change the color of my pen, and I do node 36, and I print it, so 36. Correct? So these ways of keeping down the recursive steps really helps. So let's practice that. I'm not going to write the whole tree, okay? This is too much. And So in the solution I will post after this discussion, we will have the solution of the in-order and pre-order and post-order traversal. So let's do pre-order, and give me 1 second. Let me copy the pre-order code. Yeah. In ascending order. Yes, correct. So that's the meaning of in order. Yeah. Yeah. So on the pre-order, what is the first element I'm going to visit? What is the first element I'm going to print out? 51. Okay. First. What about the second? Third one? Fourth one? Fifth one? Yeah, you get the idea, right? So I'm stepping left every single time first. So in each traversal, I'm always going to step left. So, and then step right. So the sequence is start from 51 and 12 and 1. That's all the way to the left. And then if I exhausted the left branch, then I go up to the right branch. So let me visualize it using that indentation notation. So I have like this, the whole call, and then do pre-order, PO, on the node 51, right? And then because the first line of the code is printing out, it already printed out. So the first one is 51. And then I do a recursive call because I want to set to the left. So I change color, and then do PO 12, right? And then since the first line of the call of the PO 12, so the one thing to keep in mind is if I write in those two like recursive stack, this is called recursive stack because I'm stacking everything, right? On top of each other. The important stuff is if I write PO 12, I don't care about PO 51. So you start a fresh copy of the function call. So every single function call of the PO 12, the first line is printed out the 12, right? So it goes print out the 12. And then the second line of the printing out is step to the left again. So I change color, do PO 1, and then print out the 1. And then 1 is the base case because it's just a leaf node. Then I erase it, like shorten it, because that is to the left, right? And then I need to step to the right of the 12. So in the same indentation, because this is like discontinuous, right? This is two function call. I do PO 43, and then print out 43. Yeah, you get the idea, right? This way of tracking the recursive call is really helpful. It follows the same order, right? So the one rule I have is I don't care about my parents' call because every single call is the same. So if I eventually, so the 87 should be the sixth element, right? And then 52. Because in order traversal is the same because it equals to I start a new in order traversal at 87. So it doesn't matter where I start the traversal. So if I start at 51 at the root node, I will cover every single tree, all the subtree below it, right? If I start at 87, the sequence won't change. Yeah, but only the number of nodes covered will be changed because if I start at 87, only this will be traversed, right? Because it won't go up. Yes. Yeah. Yeah. So the idea of recursion is I repeat this function a lot of times. and I start at different nodes. Yeah. And I guess the post order, you could do it on your own. I will post the answer, so you could check your answers. But yeah, the time is up, but I could do a little bit more demos for the post order, but if you are in a rush, feel free to leave. So the post order is a printed node after I visit everything, right? So what is the first node I will print out? Yeah, 1, and then? Yeah, this will be the second node. Did we finish visiting 51? Yeah. So we step here from here. Yeah, so as in the practice, in post-order traversal, the 51 will be always the last node we visit. Because in if I'm 51, like post-order 51, I will also call post-order 12, right? And then within the 12, I will call post 1. And the 1 is the base case, so I print out 1 first. So after I visit every single left branch tree, like here, I need to step to the right, because this is only the left. I need to also step to the right.
So after the 83, it wouldn't go visit 50, it wouldn't start 52, it would visit 89, right?
Repeat that?
After the 83,
Uh-huh.
visit 89, right?
It will visit 52. You will visit 52. And then 89.